Normally, in titrametric analysis, we find out the endpoint by observing a change in color of the indicator. For example, in this titration of hydrochloric acid with sodium hydroxide, our objective is to know the volume of sodium hydroxide required to neutralize a specific volume of hydrochloric acid. Once this volume is known, by using the molarity equation, we can calculate the strength or the concentration of hydrochloric acid. In such titrations, sometimes we face a few problems. For example, when we titrate very dilute solutions or in the titrations of weak acids with weak bases. In such cases, it becomes difficult to identify the endpoint during the titration because the color change is neither clear nor sharp. There may be a situation when we want to titrate a colored solution. Here also, we cannot observe the color change, therefore cannot detect the endpoint. To overcome most of these problems, we use some other properties of the solution. One such property is pH. pH is used to describe the hydrogen ion concentration in the aqueous solution. pH is equal to minus log H plus or log 1 upon H plus. In an acid-base titration, if the solution of an acid, for example hydrochloric acid, is titrated with a base, say sodium hydroxide, the hydroxide ions of the sodium hydroxide combine with the hydrogen ions of the hydrochloric acid to form water. So, the concentration of hydrogen ions gradually decreases while the pH of the solution increases. If we monitor the pH during the titration and plot a graph between the pH and the volume of the sodium hydroxide solution added, then we get a curve like this. This curve is called the acid-base titration curve or neutralization curve. In the beginning, on addition of sodium hydroxide solution, pH starts increasing slowly. At the end point, the number of moles of hydroxide ion is just enough to react completely with the hydrogen ions originally present. On further addition of sodium hydroxide, we observe a very sharp and sudden change in the pH due to the excess of hydroxide ions in the solution. From this point, we can draw a line and find the intersection of this line with the volume axis. This is the volume of standard sodium hydroxide solution used at the end point. Using the molarity equation, we can calculate the strength of an unknown acid. Now our aim is to know the pH in different stages of the titration.
This is a pH meter. With the help of this instrument, we can determine the pH of a solution. To ensure the reliability of the pH readings, the pH meter must be calibrated. To do this, it must be adjusted so that reading agree with the known standard buffers. First, we take about 20 cubic centimeter of buffer solution of pH 7 in 2 small beakers. Add sufficient quinhydron in each of the 2 beakers to saturate the 2 buffer solutions. Now, we dip both carbon electrodes in the beakers. These are 2 half cells. To complete these cells, we use agar-agar salt bridge. It contains saturated potassium chloride solution and we place it like this in the 2 beakers. We may find that the agar-agar salt bridge is not available. In that case, we can also use a strip of filter paper dipped in saturated potassium chloride solution and we place it like this in the 2 beakers. If you do use a filter paper salt bridge, remember that it should not dry out during the experiment. half cell connected with black crocodile clip is called reference half cell, and other one connected with red crocodile clip is called indicator half cell. Now we measure the temperature of the solution in reference half cell. Now temperature is about 27 degrees centigrade. With the help of the set temperature, adjust the temperature of pH meter to 27. Turn the power switch on and now put the range selector on the pH mode and slide the meter switch to 27 position. Meter should read exactly 7. We adjust it to 7 by set 0 control. Now it is 7. Bring the meter switch to standby position. Take about 20 cubic centimeter buffer solution of pH 4 and add sufficient quinhydron to make it saturated. We take out the indicator electrode and salt bridge and rinse them with distilled water. Immerse these two in the buffer solution of pH 4. In case we are using a filter paper salt bridge, remember we have to use a fresh one. Again, put the meter switch at 27 position. The meter should read 4. If it does not, then the pH knob on the back panel of the instrument is used to adjust it to 4. Now we have calibrated the pH meter. It can be checked for any other known buffer solution by replacing buffer solution of pH 4 and followed the procedure just shown. Now we will use the pH meter to know the pH during the titration. We have taken 0.1 molar sodium hydroxide solution in 10 cubic centimeter burette. Now we will take 20 cubic centimeter of vinegar solution in a beaker. Add quinhydron to make it saturated. We remove the test buffer solution and rinse indicator electrode and salt bridge. Immerse them in this solution. Now we are ready for titration. Generally, the first titration is approximate determination of the volume of sodium hydroxide needed at the end point. This can be achieved by adding sodium hydroxide in large increments, say 0.2 cubic centimeter, and simultaneously observing the pH change after each addition. Note the first reading of pH meter. Meter reading is 3 pH. Bring back the meter switch to standby position. Note the first reading of the burette. It is 0.0 at 0.2 cubic centimeter sodium hydroxide. Shake the beaker and note the reading. Meter reading is 3.3. Similarly, repeat the experiment by adding 0.2 cubic centimeter every time. Here we observe a sharp change in pH. Now note this final reading. It is 2.4 cubic centimeter. So the approximate volume at endpoint is 2.4 cubic centimeter. Based on this result, we prepare a table in the manner we will add the volume of NaOH. You can see that near the equivalence point, we will take reading by adding NaOH in small increments. Now we take 20 cubic centimeter of vinegar solution with the help of a pipette. Add quinhydron to make it saturated. Rinse indicator electrode and salt glaze and immerse them in this solution. Note the reading. Meter reading is 3 pH. Now we add sodium hydroxide solution from the burette as described earlier. At 0.2 cubic centimeter sodium hydroxide. Shake it and take the reading. Reading is 3.1. Note the pH value and the burette reading and record them in the table after each addition. After the titration is over, we plot a graph between the pH and the volume of 0.1 molar sodium hydroxide added at different stages of the titration. We can see in this plot that this portion is steepest. So, we can draw a vertical line through the steep portion of the curve and find the intersection of this line with the volume axis 2.2 cubic centimeter. This is our volume of 0.1 molar sodium hydroxide at the endpoint. But sometimes it is difficult to determine the endpoint because the vertical rise is not sharp enough. To overcome this problem, we can draw another graph between slope delta pH upon delta V and the volume of 0.1 molar sodium hydroxide solution. This table illustrates how the data for delta pH upon delta V is determined. For these readings, delta V is 0.2 and delta pH is 0.1. Therefore, delta pH upon delta V equal to 0.5. Similarly, we can calculate delta pH upon delta V for other readings. Now, plot these values on the y-axis and volume of 0.1 molar sodium hydroxide on x-axis. We get graph like this. This curve rises to a maximum at the endpoint. Now, it is quite easy to draw a vertical line from the peak to the volume axis to know the volume of 0.1 molar sodium hydroxide solution. That is 2.2 cubic centimeter. Now we can calculate the strength of acetic acid in vinegar by using molarity equation.
Conductance is another electrochemical property which can be used for titrametric analysis. It is especially useful for very dilute solutions and colored solutions. In the conductometric titration, ionic species of interest are converted to non-ionic forms by neutralization, as in acid-base or precipitation titration. In an acid-base titration, hydrogen ions react with hydroxide ions and produce non-ionic water. For an acid-base titration, if we monitor the conductance during titration and plot a graph between the conductance and the volume of the standard sodium hydroxide solution, we get this type of curve. This part of the curve, AC, is obtained when the solution is having an excess of the acid, and this part of the curve, CB, is obtained when the solution has an excess of the base. The point of intersection, C, is the equivalence point. By drawing a perpendicular from point C on x-axis, we get the volume of standard sodium hydroxide solution. Now, our objective is to know the conductance during the titration.
This is a conductometer which we use to measure conductance of an aqueous solution, and we measure it in millisiemens. Now we will titrate acetic acid of vinegar solution with standard 0.1 molar sodium hydroxide solution using conductometer. But before starting the experiment, it is necessary to calibrate the instrument to ensure reliability. First, we set mechanical zero of the instrument with the help of the screwdriver to 0. Switch on the power supply of the instrument and set mode selector on cal and range selector on 2. With the help of this sensitivity knob, adjust the reading to 1. It can be set on any desired positions like 0.2, 20 millisiemens with the help of range selector. Remember, when the range selector is switched to a new position, it is advisable to check the calibration again. This is conductance cell. Connect the wires of conductance cell with the crocodile clips of conductometer. It should be noted that with our type of cell, it is necessary to determine the minimum volume to obtain stable and reproducible conductance value.
Actually, this minimum volume for a conductance cell varies from cell to cell. This minimum volume is determined with the help of dilute potassium chloride solution. If we note the conductance with different volumes of potassium chloride and plot a graph between conductance and volume of potassium chloride, we get this type of curve. As the volume of potassium chloride increases, conductance also increases. But after this point, conductance remains constant. Draw a vertical line from this point. This is the minimum volume for this conductance cell.
For this conductance cell, minimum volume required is 17 cubic centimeter. So we will take more than 17 cubic centimeter solution. Pipette out 20 cubic centimeter vinegar solution and transfer to the conductance cell. We should know how to take reading in millisiemens at different positions of range selector. At 2 millisiemens scale, meter reading directly gives the conductance value in millisiemens. For example, suppose the meter reading is 1.2. On the 2 millisiemens scale, the conductance value therefore is 1.2 millisiemens. On the 20 millisiemens scale, multiply the meter reading by 10. For example, if the meter reading is 1.6 on the 20 millisiemens scale, the conductance value therefore is 16 millisiemens. On the 0.2 millisiemens scale, divide the meter reading by 10. Suppose the meter reading is 0.8. The conductance value therefore is 0.08 millisiemens. This is all about how to take reading of conductance. Now, we have taken 0.1 molar sodium hydroxide standard solution in 10 cubic centimeter burette. Now the apparatus is set to start the experiment. Shift the meter switch to read and note the reading. It is 0.4 at 0.2 cubic centimeter sodium hydroxide. Stir the solution with glass rod. Note the reading of conductance. Similarly, we can take 20 to 25 readings and prepare a table like this. Now we plot the graph between conductance and the volume of NaOH solution. We get the graph like this. When we start adding NaOH solution, it reacts with acetic acid of vinegar solution to give ionized sodium acetate and unionized water. This initial increase in conductance is due to the conductance of highly ionized sodium acetate. At the end point, acetic acid is completely replaced. Further addition of NaOH increases the hydroxide ions of high conductivity beside ionized sodium acetate ions. This results in sharp increase in conductance. Here, point C is the end point of the titration. Perpendicular from point C on the x-axis gives the volume of 0.1 molar sodium hydroxide used at the end point. Now, we can calculate the strength of vinegar solution using the molarity equations.
Color is another property of a solution which can be used to measure the concentration of a solution. According to Beer-Lambert's law, absorbance A is equal to epsilon Cl, where epsilon is molar absorption coefficient, C is concentration in moles per decimeter cube, and L is thickness of the medium. Here, epsilon, the molar absorption coefficient, is a constant, and if we keep thickness also constant, we can write A is proportional to C. By measuring the absorbance A for different solutions of known concentration of the same compound, we can plot a graph between absorbance and concentration. Since the absorbance and concentration are directly proportional to each other, the graph between them will be a straight line. This line is known as a calibration line. If we measure the absorbance of a solution of the same compound having unknown concentration, then with the help of this calibration line, we can find its concentration. Let us now see how we can determine the concentration of an unknown solution of copper sulfate by using a colorimeter.
This is the instrument which can measure absorbance of a solution. But before starting the experiment, similar to other instruments, we will calibrate the instrument. First, plug this 6-pin holder to the instrument. Switch on the power supply. In the cell holder, 3 LED of red, yellow, green colors are there, which can be switched on by range selector to red, yellow and green. To calibrate the instrument, first we choose the LED which gives the highest meter reading for the stock solution. In this case, we have 8% copper sulfate solution. Take this solution in the cuvette. See, a cuvette has 2 plane sides and 2 straighted sides. We have put a mark on one of the plane side. Now insert the cuvette in the cell holder with the mark side facing the LED inside the holder. Remember, during the experiment, always insert the cuvette in the same way. Close the cell holder. Now range selector on green and the reading is 1. On yellow, the reading is again 1. And on red, it is 6. And that is the highest. So we will keep the range selector on red. At the same time, with the help of sensitivity knob, we adjust meter reading to the end of scale, say 9. Now we will take distilled water as a reference solution in the same cuvette after throwing copper sulfate solution. And washing with distilled water. And insert the cuvette in the same manner in the cell holder. With the help of set 0, we will adjust the meter reading to 0. Now instrument is ready for experiment. Now take out cuvette from the cell holder and throw the distilled water. And rinse it twice with 8% copper sulfate solution. Insert the cuvette in the cell holder in the same way. Now meter reading is 6.5. Similarly, we repeat the experiment with other solutions of known concentrations and of course with the unknown copper sulfate solution. Note all the reading in the table and then plot a graph between meter reading and percentage of copper sulfate solutions. Meter response for unknown solution was 4.6. Draw the line on the graph to get concentration of the unknown solution. In our case, it is 5.7%.
So far we have shown you the low-cost instruments. Before we end this program, we would also like to show you the commercial instruments. This is a digital pH meter. In place of carbon quinhydron electrode, we use one combined electrode. Before use, similar to previously used pH meter, this pH meter is also calibrated with known standard buffers. To measure the pH, we dip the electrode in the solution. The result is immediately displayed on the meter. This is a commercial conductometer with conductivity cell. When we use this instrument to measure the conductance, the clean conductance cell is rinsed with distilled water and then dipped in the solution whose conductivity is to be measured, and the required result is immediately displayed on the meter. This is a spectrophotometer. By using this instrument, we can measure the relative absorption of light even in ultraviolet region. Instead of colored filter or colored LED, we use a range of wavelength. Similar to low-cost colorimeter, we first calibrate this instrument. This is the sample holder. Close the sample holder and set 0. Place a cuvette approximately half filled with a reference blank, that is distilled water or an appropriate solvent. Set reading at 0 absorbance. Remove the reference blank and put the test sample and note the absorbance. We repeat this exercise by changing the wavelength. We plot a graph between absorbance and wavelength and determine lambda max. At lambda max, the absorbance of the solution is the maximum. The selection of lambda max is similar to the selection of LEDs in the colorimeter. Similar to colorimeter experiment, construct a calibration curve using known sample at this wavelength and determine the concentration of the unknown sample. In this program, we have discussed about the 3 instruments which are used in quantitative analysis. Discuss with your counselor which method is the best method in a given situation.